Hello, guys. I'm happy to be here to share my project with you guys. My name is Zijin Liu. I'm from Purdue University. Um, Here's my outline. Our main goal is visualizing Brownian motion on S3. So S3 is basically a three sphere lies in R4, and Hopf fibration is a special kind of mapping. Well, I'll introduce those later. So there are two important parts in my project. The first one is geometry, and the second one is Brownian motion. Okay, let's get started with geometry first. Before I introduce Hopf fibration, I'm gonna tell you guys what Sn is. Sn, which is also called n-sphere, is an n-dimensional sphere lies in Rn plus 1. So in particular, S1 is the circle and S2 is just a regular sphere. And then the Hopf fibration is a fiber bundle. We can write it as S1 to S3 to S2. So in this part, S3 to S2 is a Hopf map. Hopf map is a many-to-one continuous map from S3 to S2, which is given by this. So in this map, we let the first coordinate to be 0, and the next three coordinates is given by these formulas. One can check that the sum of the square root of these three coordinates is 1. So it lies on a sphere, but it's three-dimensional because the first coordinate is 0. So it's a three-dimensional sphere, and that's S2. So that's why Hopf's map is from S3 to S2. And why there's S1 here, that's the definition of fiber. For each point in S2, the pre-image under the Hopf fibration, which is this, is a circle in S3. So we can prove that. So the circle is S1, as I said before, and we call the circle fiber. So the fiber is S1, and the Hopf's map S3 to S2. That's why we write it as S1 to S3 to S2. And the difficulty is, although S3 is three-dimensional, it lies in R4, but we can now visualize the 4 space. So in order to visualize it, we need to introduce stereographic projection. So let's do two-dimensional case first. A two-dimensional stereographic projection is a map from S2 to R2 plus the infinity. So here's the projection, here's how the projection works. So for each point on the sphere, we can connect this point with the south pole, and we connect the 2 points and extend this line until it intersects with R2, the two-dimensional plane. And this point on R2 is the image of this point. So that's how the projection works. And this projection map each latitude to a circle on R2. But there's still one point left, which is the south pole. So we define the image of south pole to be infinity. That's why we say the two-dimensional projection is a map from S2 to R2 union infinity. That's the south pole. And so similarly, this three-dimensional case is a map from S3 to R3 union infinity. Then we can visualize the 3 space using stereographic projection. But another difficulty is that one could not visualize the whole 3 space because it's unbounded. For example, if there's a curve, unbounded curve, then it's pretty hard to use computer software to visualize such a curve. Then to solve this, we define modified stereographic projection, which is given by this. So let's look at this part first. This part is actually a normalization of XYZ because remember, x squared plus y squared plus z squared plus w squared is 1 because it lies in S3. So 1 minus w squared is the sum of x squared, y squared, and z squared. So this part has magnitude 1. And the coefficient here ranges from 0 to 1. That's because W ranges, W lies in S3, so W need to be between -1 and 1. So our cosine ranges from 0 to pi. Then you divide it by pi. So this coefficient ranges from 0 to 1. So it's positive and less than 1. And this part has magnitude 1. So the whole f of q must lies inside the unit ball. So fq is always in D3. D3 is just a unit ball in R3. So then it's easier to visualize a bounded space because, of course, unit ball is a bounded space. So after this, those mapping, here's what we get for Hopf fibration. Like for each point in S2, it corresponds to a circle here. And I picked the horizontal circle in S2. So for each point, it's corresponding to a circle. And then the circle in S2 corresponding to this, it is a torus. Yeah, that's the Hopf fibration in 3 space using modified stereographic projection. It's a closed torus. So then the next key point is change of coordinates. Well, for a point in S3, so there are, in our regular Euclidean space, we use 4 coordinates like x1, xyz, xyz, w. But there is a way that we can use 3 coordinates to describe a point because it's 3-dimensional. And here's what we have. So pick a point, say W in CP1. Well, CP1 is just is isomorphic to S2, so they are almost same. So CP1 is almost like a sphere. Then it corresponds to a circle in S3 under the sense of Hopf's map, as I said before. So then we can pick a point theta on that circle. Then we can identify a point UV theta in S3, where the UV is the real and imaginary part of W. So the advantage of this frame is that first, it involves the fibration structure inside this coordinates. And the second one is, as I said before, we only use 3 coordinates to describe a point in S3. So that's why we choose this coordinates. And the formula between the regular Euclidean coordinates and this is given by here. So Z1 is W times e to the I theta over 1 plus W square, and Z2 is e to the I theta over the square root of 1 plus W square. So this actually corresponding to 4 real number, because for each Z, there it has its real part and imaginary part. So then 2 of them has correspond to 4 real number. That's correspond to its regular Euclidean coordinates. Okay, so next part is the Brownian motion, because, well, of course, our project is visualizing a Brownian motion. So Brownian motion is also very important. Brownian motion of a particle is caused by a collision with a large set of other particles. It's a natural phenomenon, but Wiener, a mathematician, gave a rigorous definition using stochastic process. So Brownian motion is also called Wiener process. In order to visualize the Brownian motion, we may use random walk and the central limit theorem to approximate it. So here's what we did. So first, consider like n random variables where the probability of it equals 1 equals to the probability equals to -1 is 1/2. Actually, each xi is a step. Like we can go left or right with the same probability. Then by central limit theorem, so if you sum those and divide it by square root of n, by central limit theorem, it will converge to a normal distribution as n goes to infinity. So here's the key point we use to visualize Brownian motion. here's the 1D Brownian motion. That's we use CLT and random walk to do this. So once you increase the step, which means you decrease the step size, then the random walk will become a Brownian motion. So here's the 1D Brownian motion. And for 3D, it's not hard because we can put each coordinate to be a 1D Brownian motion and then modify it a little bit to get a 3D Brownian motion. So here's a 3D Brownian motion. Okay, so now it's our key algorithm to construct the Brownian motion on S3. So first, we construct 4 independent 1D Brownian motion, B1 to B4, then B1 plus I times B2, comma B3 plus I times B4 is a Brownian motion on C2. Then it can be proved that W of T, which is given by B1 plus IB2 over B3 plus I times B4, is a Brownian motion on CP1. Well, recall that CP1 is just almost same to a sphere. And then the Hopf fibration has a degenerate structure. That is, we can only control the movement in 2 dimensions, like the U and V here, but the 2-dimensional movement can still cause 3-dimensional increment. The extra increment theta of T is given by the stochastic area swept by the path on CP1. So here is a picture, it may help you to understand this. So it's like, so the shaded area is the stochastic area, and then it equals to the extra increment for this path. Okay, and the area, the formula of the area is given by this. So we use this to calculate the area of the just the stochastic area. And then we use the change of coordinate formula as said before to get the Brownian motion on S3 in Euclidean space, because what we have now is U and V and theta. That's the another frame of coordinates. So, but we want to visualize it in our Euclidean space. So we need to map it back to our regular Euclidean space. The next, we use the modified stereographic projection to map the path to 3 space to visualize it, and then use the Hopf map to map the path in R3 to S2 to get the Brownian motion on the sphere. So we basically have two plots. The first one is the path on S2, and the second one is the path on S3, but after stereographic projection. So here's what we get. This is our main result. Is a Brownian motion on S3, but after a modified stereographic projection. So it's locally like regular 3D Brownian motion. And here is the Brownian motion on S2. So for each point here, it corresponds to a fiber here. Well, actually, our project is only in middle, so I could not give you much explanation on this. But what we had is just, as I said, is locally like a 3D Brownian motion, and in the future we will try to give some more explanation about this. So here's our future plan. So we will draw some fibers in the plot, like the Brownian motion on S3 to see how it works. And next we will replace the Brownian motion on CP1 by some testing curve, like smooth curves, because the Brownian motion is involves some randomness. So we want to use some smooth curve to replace those randomness to see how the mapping works and explore the more properties of the of those mapping I said before. Okay, that's all. Thank you for listening.